Okay, so here we're going to start our journey into chemical equilibrium. So the first thing that we need to say about equilibrium is that chemical equilibrium is the condition where the forward and reverse reactions are occurring at the same rate. All right, and so often when we're talking about equilibrium, right, or really from this point of the class forward, when you see a chemical reaction, you will see an arrow that looks like this, right? Two half arrows, one pointing one way, one pointing the other, in between like A plus B and D plus E, right, to indicate that the forward and reverse reaction are occurring. And so that's what we will be taking a look at, and really what is going on here with chemical equilibrium is that it is dynamic, which basically means that the reaction does not stop, right? Doesn't stop, but the concentration of the reactants and products is no longer changing, right? So it has reached a steady state as far as the concentrations go, but the reaction has not stopped. It is still going in both directions. So let's look at an example, right? So how we get to equilibrium. When we're talking about this, right, this is how we might write a chemical equation, right? Our N2O4 is making two NO2s. And if we were looking at the rate of this reaction, right, and we were saying the rate is equal to, or rate of the forward reaction is equal to K sub F times the concentration of N2O4, right, we would also say that the reverse reaction, or the rate of the reverse reaction, is equal to K sub R times the concentration of NO2 squared. Now, if we put these both together, right, we say that K sub F over K sub R, or the equilibrium constants, or the rate constants there, sorry, my brain is in equilibrium mode, the rate constants there are equal to the concentration of NO2 squared over the concentration of N2O4, and that if these are at equilibrium, right, this will be constant, right? These things will not change, right? The concentrations will be constant, and that this whole thing should equal a constant. All right, so hold on to that thought. So if we have this reaction, right, we put this in place of our N2O4 and NO2 reaction, right, then we can write an expression like this, which looks very much like our other one where we had our NO2 squared over N2O4, right, and have it equal to a constant right here, an equilibrium constant, where we have, right, our products over our reactants, however you spell reactants, and each of them is raised to the power of their balancing number, right? So like A with a balancing number of A becomes concentration of A to the A, right? And that's what these brackets are telling us, concentration. In fact, you know what? Let's get rid of this and bring this up, right? K sub C is the equilibrium constant, and everything there, right, anything in the brackets is the concentration of the chemical species in moles per liter, right? And so this is how we always write it, right? Always written as products over reactants. Don't forget that. Products over reactants. Always, always. Right? And so this is when we're talking about concentrations. So we can also express equilibrium when we talk about gases and pressure, right? So when something is in brackets, it denotes concentration. When something is in parentheses, it denotes pressure. And the conversion between the two, right, because we can relate the two, pressure and concentration, we're looking at it, is we have RT, which should be a familiar term from our gas laws unit, right, where we have the equilibrium constant dealing with pressure is equal to the one dealing with concentration times RT raised to the change in the number of moles, right? And anytime you have change in, right, you're looking at final minus initial or products minus reactants, right? Final minus initial. And so just as an aside, why this works, right, is because if we're looking at pressure, right, and we rearrange the ideal gas equation, we have nRT over V, and if you have N over V RT, right, what is this? This is moles. What is this? This is liters, right? And that is concentration. So pressure is equal to the concentration of some species times RT, right? Which we've got concentration, or a concentration constant, times RT raised to the power of the number of moles, right? And so that is why we can make that switch there. And so when we're looking at things dealing with pressure, this is going to look a little different, but not much, right? So you will notice that here we are looking at pressures, and notice I'm going to draw lots of arrows here to the parentheses. So I know that this is going to be one of those things where you're like, why are you drawing all those arrows to the parentheses? And it's because when we are working with pressures in an equilibrium expression, you put the numbers in parentheses, not brackets. Parentheses, not brackets. Parentheses, not brackets. For whatever reason, when we're working with equilibrium, you don't put pressures in brackets, you put pressures in parentheses. Other than that, the equilibrium expression works exactly the same. It is still products over reactants. K sub P is still an equilibrium constant. It's just that now we have the pressure of the chemical species in units of atmospheres. Right, so that's the difference between working with concentrations and pressures dealing with equilibrium. So now we know our states, right? Solid, liquid, gas. Okay, yeah, plasma as well, but we're not going to deal with any plasmas. And it becomes important that we know what state something is in our chemical reaction when we are dealing with equilibrium, because equilibrium expressions do not contain pure liquids or solids, right? And remember that, so our abbreviations here are S for solid, L for liquid, G for gas, and AQ for aqueous. So that is something dissolved in water. So equilibrium expressions do not contain either of these first two things. Anything that is listed as a pure liquid or a pure solid does not appear in an equilibrium expression. So, for example, if we have this sort of situation where we are dissolving lead chloride in water to form an aqueous solution of lead ions and chloride ions, when we go to write an equilibrium expression for this solution or the dissolution of lead chloride in water, we write it as this, right? We just put lead ions and chloride ions in here, right? There is no bottom here, right? There's no stuff down here because this is a solid and it does not appear in an equilibrium expression. As another example, if we have the synthesis of water by mixing of hydrogen gas and oxygen gas, right, our equilibrium expression for this is going to be right here because water is a pure liquid, so it will not appear here on top in our equilibrium expression, right? We only have our reactants on the bottom because those are gases which do appear in equilibrium expressions. And so that is what we have to keep in mind when we are writing equilibrium expressions for various reactions, that expressions only contain gases and aqueous solutions. They do not contain liquids or solids. Okay, so I think at this point you're probably asking, great, why should I care? Which I will tell you, you should care because using equilibrium expressions, you can tell if a reaction favors the formation of products or reactants given current conditions. You can tell if a reaction has reached equilibrium based on current conditions of reactants and products. It can be used to determine how much of a substance will dissolve in a given situation, or you can tell the solubility of a given substance. And you can figure out all kinds of great acid and base chemistry stuff using equilibrium. In fact, a lot of acid-base chemistry, and particularly buffers, is all equilibrium chemistry. So for these and many more reasons, you should care about equilibrium. But now I will leave you there, and we will talk about ice tables and what we do with equilibrium expressions and numbers in the next video.